Wormholes are one of science fiction's favourite toys. Convenient, awe-inspiring, a neat shortcut across impossible distances of space, and sometimes even time. But what's the truth about them? Where did the idea actually come from? Are wormholes real, or just mathematical curiosities that physics quietly refuses to allow? And if they do exist, could they break the most fundamental rule the universe seems to obey? Cause and effect. Mathematics says yes. Reality may strongly disagree. This is Dark Beacon, and in this video, we're exploring the truth about wormholes. Wormholes weren't dreamed up by science fiction. They slipped out of the mathematics. When Einstein finished General Relativity, he rewrote gravity itself. No longer a force acting at a distance, but a consequence of geometry. Mass bends spacetime. Spacetime dictates motion. Clean, precise, unforgiving. And then the equations began to say things Einstein didn't like. When physicists pushed those equations into extreme territory, they found solutions that did more than curve spacetime. They connected it. Two distant regions of the universe joined by a narrow mathematical bridge where none should exist. Einstein didn't celebrate this. In 1935, working with Nathan Rosen, he described the idea cautiously, not as a doorway, but as a fragile structure. A bridge that formed and collapsed almost instantly. A feature of the mathematics that felt more like an error than an invitation. But equations don't care about discomfort. Once the solution existed, it couldn't be erased. General relativity allowed space-time to fold, to overlap, to connect regions of the universe that should never touch. And that was only the beginning of the problem. Because a bridge through space-time isn't just a shortcut through space. It's a shortcut through order, through sequence, through cause and effect. If structures like this were ever real, they wouldn't just change how far things are apart. They would threaten the one rule the universe seems to enforce above all others. The rule that the past stays in the past, and the future arrives only once. And that's where wormholes stop being interesting and start becoming dangerous. A wormhole isn't a tunnel cut through space. That image is useful for films, a pencil poked through a folded sheet of paper, but it's a simplification that borders on a lie. In reality, we don't live on a two-dimensional surface. We live in a three-dimensional volume of space, embedded in space-time. If you were to stand in front of a real wormhole, you wouldn't see a hole at all. You would see a sphere, a floating three-dimensional orb, like a window, reflecting a sky from millions of light years away across its curved surface. This idea didn't appear in isolation. It emerged from the darkest corners of general relativity, the mathematics of black holes. When Einstein and Nathan Rosen studied the equations of a non-rotating black hole in 1935, they noticed something unsettling. The mathematics didn't just describe a dead end, it described a bridge. The fabric of space-time could, at least in theory, be bent so severely that it connected two entirely separate regions of the universe. This was the original Einstein-Rosen Bridge. But Einstein didn't design it for travel. In fact, he found that the bridge was non-traversable. Gravity is relentlessly attractive. It always pulls inward. The moment this bridge forms, the sheer weight of space-time causes the throat to pinch shut. It collapses so fast that even a single photon, the fastest thing in existence, would be crushed before it reached the other side. To an outside observer, it looks indistinguishable from a black hole, a one-way trip to nowhere. But the implication remains. The equations suggest that space is not a rigid stage, it is a fabric that can be folded. A wormhole is simply the geometry of two distant places being forced to touch. It isn't about moving faster than light, it's about making the distance shorter. The mathematics says the door is there, it just insists the door is locked from the inside. And that's what makes wormholes so haunting. They aren't a violation of the rules, they are a feature of the system. The question was never whether the universe could form a bridge, it's whether anything could stop the universe from tearing it down. In practice, a natural wormhole behaves less like a doorway and more like a trapdoor. The geometry that briefly connects two regions of spacetime is violently unstable. The intense curvature causes the throat of the wormhole to narrow and snap shut, sealing the connection almost as soon as it forms. What remains looks indistinguishable from a black hole. From the outside, there's no sign a bridge ever existed. No tunnel, no passage. Just space-time collapsing inward, obeying gravity as it always does. This is why early wormholes were dismissed for decades. Not because they were forbidden, but because they were useless. They formed, they collapsed, and nothing could ever pass through them. In other words, general relativity allows wormholes, but only in the most unhelpful way possible. If a wormhole appears naturally, the universe closes it immediately, which leaves only one uncomfortable possibility. If a wormhole were ever to stay open, something would have to actively hold it there. And whatever that something is, it would have to fight gravity at its most extreme. If a natural wormhole collapses the moment it forms, then keeping one open would require intervention. Something would have to push back. Gravity doesn't negotiate. It pulls spacetime inward, tightening curvature until the throat of the wormhole snaps shut. To resist that collapse, you'd need something that does the opposite, something that forces spacetime apart. This is where physicists introduce a name that sounds like science fiction: exotic matter. Despite the name, exotic matter isn't a specific substance, it's a mathematical requirement, a label for whatever kind of matter or energy would be capable of producing the negative energy density needed to stabilize a wormhole. On paper, it works beautifully. Allow exotic matter into the equations, and a traversable wormhole can exist. The geometry holds, the throat stays open, the maths balances. But that elegance hides a problem. Nothing we know how to create behaves this way at scale. Quantum physics does allow tiny, tightly constrained regions of negative energy, effects measured in laboratories under extreme conditions. But these are fleeting, microscopic, and fragile. They vanish the moment the constraints are relaxed. A wormhole wouldn't need a hint of exotic behavior. It would need vast quantities of it, sustained, carefully arranged, actively maintained. A stable wormhole wouldn't be a passive structure. It would be like holding open a tightening vise with a wooden block. The force never stops, and when it fails, it doesn't fail quietly. Exotic matter wouldn't create stability. It would apply constant outward pressure. Under continuous stress, one slip away from catastrophic collapse. Which means exotic matter doesn't solve the problem. It just gives it a name. If you're finding this interesting, a like helps more than you might think for a small channel like Dark Beacon, and if you've got thoughts or questions, I do read the comments. Now, let's continue. Even if you imagine exotic matter somehow holding a wormhole open, there's another problem waiting. Space-time is never empty. Even in a perfect vacuum, quantum fields are constantly fluctuating. Energy briefly appears, disappears, and reappears again. This isn't unusual or exotic, it's simply how quantum fields behave. In ordinary spacetime, these fluctuations are harmless. Their effects balance out almost perfectly. Tiny disturbances arise, cancel one another, and fade away before anything can accumulate. Over time, the net energy remains essentially zero. That balance depends on spacetime being gentle and open. A wormhole throat is neither. It's an extreme geometric bottleneck, a region of spacetime that is tightly curved and highly confined. In that environment, quantum fluctuations don't behave normally. As light or energy enters the throat, gravity accelerates it, blue shifting it to higher and higher frequencies, packing more energy into every wave until the bridge itself can't handle the load. The energy doesn't vanish, it compounds. Each fluctuation adds a little more energy to the throat. That added energy increases the local curvature of spacetime, which makes the next fluctuation even more energetic. What should have been harmless background noise becomes a growing instability. A feedback loop forms. More curvature amplifies quantum effects. Amplified quantum effects add more energy. More energy increases curvature further. There's no natural braking mechanism. As the energy density rises, gravity around the throat strengthens. The exotic matter holding the wormhole open becomes overwhelmed. The harder you try to maintain the structure, the more violently the quantum vacuum pushes back. This isn't a minor correction or a technical nuisance. Calculations show that the energy near a traversable wormhole would grow without bound, until the structure destabilizes completely. At that point, one of three things happens. The wormhole snaps shut violently, or it collapses into a black hole, or quantum effects become so extreme that our current theories simply stop working. None of these outcomes are survivable. So when physicists say quantum mechanics destabilizes wormholes, they don't mean it makes them inconvenient. They mean the quantum vacuum itself becomes an amplifier, turning the wormhole into a focus for runaway energy until spacetime can no longer hold the shape you forced it into. Even if exotic matter exists, even if you pay the price, the quantum fields are still there, and they will not stay quiet. Up to now, every problem with wormholes has looked technical: collapse, exotic matter, quantum instability. But beneath all of it lies a deeper issue. A stable, traversable wormhole wouldn't just connect distant regions of spacetime, it would connect different moments within it. Because space and time are inseparable, any shortcut through spacetime is also a shortcut through temporal order. If the two mounds of a wormhole experience time differently, through motion, gravity, or acceleration, they fall out of sync. At that point, the wormhole becomes more than a bridge across distance, it becomes a bridge across time. Step through one end, and you could emerge before you entered. This isn't science fiction, it follows directly from the mathematics. The moment a traversable wormhole exists, closed loops in time, known as closed time-like curves, become possible. And that's where physics becomes uncomfortable. Cause and effect lose their clear ordering. Events no longer flow cleanly from past to future. Paradoxes aren't hypothetical edge cases, they are built into the structure. In the 1990s, Stephen Hawking proposed what he called the Chronology protection conjecture. Not a law, not a proof, a suggestion. The idea was that the laws of physics might prevent time travel, not deliberately, but through instability. Any attempt to form a space-time geometry that allows causality to loop back on itself would trigger effects that destroy the configuration before the violation can occur. But this was a conjecture. We don't know that space-time has a built-in protection mechanism. We don't know that the universe cares about causality in that way. What we do know is this: every known attempt to construct such a wormhole, in theory, runs into the same wall. In the mathematics, energy densities diverge. Quantum effects grow uncontrollably. The geometry destabilizes. Whether that's enforcement, or coincidence, or a sign that our theories are incomplete, we don't yet know. What we can say is that the resistance is real. Natural wormholes collapse. Exotic matter demands the impossible. Quantum fluctuations refuse to stay quiet. Again and again, the mathematics points toward the same outcome. Not a clear prohibition, not a cosmic rulebook, but a pattern of failure that appears precisely when cause and effect would unravel. So maybe spacetime isn't protecting itself. Maybe we're just seeing the limits of theories that were never meant to be pushed this far. So where does that leave wormholes? They aren't fantasy, And they aren't engineering projects waiting for better tools. They are allowed by our best theory of spacetime. They appear naturally in the mathematics. And yet, every time we try to make them real, even on paper, the same pattern emerges. Natural wormholes collapse. Keeping them open demands conditions reality barely tolerates. Quantum fluctuations refuse to stay quiet. And when time itself becomes entangled, the equations begin to unravel. Shortcuts don't fail because we lack imagination. They fail because spacetime resists being rearranged that way. That doesn't mean wormholes are impossible. It means they sit at the edge of our understanding, where geometry, quantum mechanics, and causality all strain against one another. In that sense, wormholes may not be gateways. They may be stress tests. They show us where our theories stop cooperating, where smooth spacetime gives way to instability, where cause and effect stop being negotiable. And maybe that's their real purpose, not to take us somewhere else, but to show us where the universe refuses to go. See you next time.